Now let's see some examples in section 68. Actually, two problems from exercise. The first is exercise number 9. That is, suppose that a series given by this summation n is equal to negative infinity to infinity x square bracket n times g to the negative n converges to an analytic function x of g in some annulus. Absolute value of g is greater than R1 and less than R2. That sum x of g is called the G transformation of x of square bracket n, where n is 0, plus minus 1, plus minus 2, keep going like this. The problem is use expression 5. Here I wrote it here. In section 66, for the coefficient in Laurent series to show that if annulus contains the unit circle, absolute value of g is equal to 1, then the inverse G transformation of x of g can be written by this x square bracket of n is equal to 1 over 2 pi integral negative pi to pi x of e to the I zeta times e to the I n zeta d zeta, where n is 0, plus minus 1, plus minus 2. Keep going like this. Okay, the problem is required to show this holes. Yeah, suppose that summation n negative infinity to infinity x of square bracket n g to the negative n converges to an analytic function x of g in some annulus given by this. The absolute value of is greater than R1 and less than R2. If this annulus contains the unit circle C, which is parameterized by g is equal to e to the I zeta, where zeta is greater than or equal to negative pi and less than or equal to pi, then we have this x of g is equal to, from this in the problem, and also which is equal to this comes from Laurent series in section 66, where Cn is given by this. Then here x of n is equal to c negative n. Here n is replaced by negative n. Then we can write this. Because here is t to the negative n. So x of n must be equal to c negative n, which is Cn is equal to 1 over 2 pi I integral along to c fg dg divided by g negative g naught to the n plus 1. So if we n is replaced by negative n, then here n is replaced by negative n, then we get this. Because we consider the unit circle C parameterized by g is equal to e to the I zeta, we replaced, we plug in this form in this and this and this. E to the negative n plus 1 is equal to e to the I zeta. G to the negative 1 plus 1 is equal to e to the I zeta to the negative n plus 1, then we arrange this part, and we get this e to the negative n I theta times e to the I theta. Okay, this part is the same here. Then we cancelled e to the I theta, and r is also cancelled by this part denominator. So we get this 1 over 2 pi times integral negative pi to pi. Here g is replaced by e to the I theta, so we get this x of e to the I theta times here e to the negative n I theta. We get this. Then 1 over e to the negative n I theta is equal to e to the n I theta, because this part is equal to 1 over e to the n I theta. Then we get this identity. So here we get this. Actually, from this equality, we get this dg is equal to I times e to the I theta d theta by differentiating both sides. Okay, then this is the desired result for the problem 8.